Hi everyone. Let's do another example using Ksp. Remember, in the problem that we just did, we calculated the solubility of silver chromate in deionized water, and I think we got 6.6 with an insignificant 9 times 10 to the -5th molar for the solubility. So let's do a very similar problem where we calculate the solubility in half a liter of a solution containing sodium chromate. Again, no matter what problem I'm faced with, I'm going to write down the reaction first. Silver chromate is in equilibrium with 2 moles of silver and 1 mole of chromate. And I'm going to set up an ice table. And again, just to be very clear, I am going to sketch our initial conditions. Again, we might have a jar of silver chromate on the lab bench. And this time, rather than just having a beaker of water, we do have a solution that has sodium ions and chromate ions. So what I'm noticing is that the solution and the salt have an ion in common. So this is the so-called common ion effect. And how does that affect this equilibrium? Well, you've increased chromate in the solution, and according to Le Chatelier's principle, that's going to shift this equilibrium to the left. So in the presence of this common ion, we would expect the solubility to decrease. So if we get a solubility greater than this number here, we might want to be concerned. So again, we expect the solubility to decrease. So let's describe our initial conditions again. Do we have any silver in this beaker? No, that's because we haven't done anything yet. But do we have any chromate in this beaker? Yes, we do. We have chromate from the sodium chromate, and its concentration is 0.10 molar. Again, I'll just write the word solid for silver chromate. So now we're going to actually pour the salt into the beaker. The salt goes down by X, silver goes up by 2X, chromate goes up by X. So at equilibrium, we have 2X for silver and 0.10 molar plus X for chromate. So now we'll write our Ksp expression. That'll be the concentration of silver squared. And that's also times the concentration of chromate. So if I distribute the 4x squared across these two terms, I think I end up with 0.40x squared plus 4x cubed. And now I'm worried because I haven't solved an equation like this in a long, long time. I'm not a mathematician. But as a chemist, I think I can simplify this problem just a little bit. If we think about the magnitude of this x, isn't it going to be so much smaller than the 0.1 molar? Isn't this x going to be a lot less than the 0.1 molar? That's because this equilibrium lies to the left. This is chromate coming from silver chromate, which isn't that soluble to begin with, and its solubility is going to decrease in the presence of the common ion. And this is chromate from the sodium chromate. So I have a feeling, and I think it's reasonable to assume that this X is going to be much less than 0.1 molar, and that really simplifies things. Now, when we write our Ksp, Ksp is equal to the concentration of silver squared times 0.1 molar. And that'll be 4x squared times 0.1, so 0.40x squared. Solving for x, I think that'll be the square root of the solubility product, which was 1.2 times 10 to the -12th. And we have to divide by 0.4. And when I did the arithmetic, I got 1.7 with an insignificant 3 times 10 to the negative 6 molar. That is the solubility. And do you remember what it was in deionized water? It was this, 6.7 times 10 to the negative 5th. So yes, the solubility did decrease in the presence of a common ion. So hope you enjoyed the video, and thanks for listening.